The next topic I called computing covariance matrices, just because I couldn't really think up a better title for it. So in the third topic, I talked about what a variance-covariance matrix is, and now I want to show that really what we're doing when we do matrix multiplication, you can sort of design one matrix to operate on another matrix to give you what you want. And so this, the covariance matrices gives kind of a nice way to explain that and also to discover that some matrices have very interesting properties. So let's take a closer look at how we made this x tilde vector. So I said x tilde was equal to x, so this is a column vector with m elements. X bar was a scalar, and E was a column vector of m1s. So when I do this multiplication here, I just end up with a vector of length m, and every element of that is equal to x bar. And then when I subtract that from x, it gives me, I call it a centered vector, because now it's going to have sample mean 0. And now I want to work backwards a little bit. So I'm going to replace x bar by my, I guess, matrix definition, my matrix computation that gave me the sample mean. And now it might get a little bit more clear why I wanted to put the x bar after the e. So if you look closely at this, I have this column vector, and then this row vector, and then this column vector here. And then the 1 over m, that's a scalar. And remember, so a column vector, that's just a matrix with one column and m rows. This is a matrix with one row and m columns, and then m rows and one column again, and a scalar. And for matrices, I'm free to do the multiplication in any order I want to. So if I did this multiplication first and then divided by m, I ended up with x bar. But let's look at what happens if well, let's see what I did exactly. Yeah, so I'm going to instead look at this matrix now, E transpose. So E is this column vector of m1s. E transpose is a row vector. So I'm going to end up with a square matrix, m by m matrix of all 1s. And then I'm going to divide that by m and multiply that by x. And that's going to be equal still to x tilde, because I'm still doing the same operation. I'm just kind of organizing the computations in a different order now. And now I'm going to factor, so I can factor always an identity matrix out of something. So I could write this as I, so now I have an m by m identity matrix I, minus E transpose, so this outer product here is an m by m matrix of all 1s divided by m. So each element of this second matrix is 1 over m. And now I'm going to think about this thing, the identity matrix minus E transpose over m. Think about that as A, so I can write x tilde here as a matrix A times x. So I'm designing this matrix A to subtract the mean from my vector x. What is A? So the outer product, E transpose, is an m by m matrix. I is the m by m identity matrix. So A is also going to be an m by m matrix. And it's this special m by m matrix that has the property that pre-multiplication, so I mean multiplying, I put A before x, that's pre-multiplying, turns x into x tilde. And so you can think of this matrix multiplication now as one matrix acting on another. So we saw things like this already with a permutation matrix. I pre-multiply by a permutation matrix, and that swaps rows. also, I think I showed a rotation matrix at some point. So I pre-multiply a vector by a rotation matrix, and that just rotates the vector. So there are certain matrices, you can design them to do something that you want. And so I've designed this matrix A to center the vector x. So I want to subtract the sample mean from each element of x. So now let's consider what happens when I pre-multiply the matrix R by A. So remember, R was this matrix I made that had one column x, the first column is x, and the second column is y. So I have my matrix A, so that's where this A comes from, and then R is this matrix with column x and column y. And so I can think of R as having a block structure where the blocks are just going to be the columns. So when I do the multiplication, the first column is just going to be A times x, and the second column is going to be A times y. And then we know what A does to each of these vectors. So A turns x into x tilde, and A turns y into y tilde. So when I do this matrix multiplication here, I'm going to end up with x tilde, y tilde. So this same matrix A is going to turn the matrix R into R tilde. So now let's think about what's going to happen when we stick this into our expression for the covariance matrix. So in the previous set, I had to define the covariance. I needed to subtract the mean, and then I could calculate the variances and covariances. So I needed to first make this matrix R tilde, and then I could compute the covariance. So here I'm aiming to get the covariance of the matrix R, the sample covariance for the matrix R. But I first need to make this R tilde matrix in order to do that. But now I can replace R tilde just by AR, because A is going to turn R into R tilde. And now I have a product here and a transpose, so I might as well use my transpose rules. Oops, I guess I'm getting ahead of myself. So let's see. Since R has two columns, the covariance matrix for R is going to be a 2 by 2 matrix. Okay, so in general, so I guess what I wanted to communicate here was I'm trying to do a 2 by 2 matrix just to keep things simple. What's going to happen in general is that, so here R has two columns and R tilde has two columns, and because I can just apply A row by row, sorry, these are columns, I can apply A column by column. I could do 3 columns. I could have had an arbitrary number of columns in R, so I can say it has n columns. And so if R has n columns, then the covariance matrix for R is going to be an n by n matrix. And what you'll end up with then is the diagonal elements are going to be the variance, the sample variances for the columns, and then the off-diagonal elements will be the sample covariances for that particular row and that particular column. And the nice thing about this is the A only depended on the number of observations. So it only depended on the number of rows in R. So it was the length of each one of these vectors, M, because it was I minus EE transpose over M. So this matrix A stays the same regardless of what how many columns I decide to put into R. Okay, so now I get to do my exciting result. So I'm looking at the covariance matrix for R. And on the last slide, I said, well, I can write that as AR, that product transposed, times AR, because AR is equal to R tilde. And now I have a rule for taking the transpose of matrix products. So I can rewrite this as, so 1 over M, my scale factor, R transpose, A transpose, AR. And so now what I want to do is, usually when you see something like this, remember when I was saying when you have a matrix transposed times itself, it'll be symmetric. It also sometimes has nice properties. And so let's take a look at that and see if we can find anything interesting. So product A transpose A is just going to be, all I've done here is I'm replacing A by how I created A in the first place. So that's I minus EE transpose divided by M. And so I have A transpose A. And now here's a transpose again. I've got a product here and a sum here, and I have rules for taking transposes of that. So let's try that and see what happens. So let's see if I did that. So the first thing I did was transpose of a sum was just the transpose of each part of the sum, each term in the sum. So this sum transposed becomes identity matrix transposed minus EE transpose over M transposed. Identity matrix transpose, so it's diagonal, it's symmetric, transpose is equal to itself. So this will become I, and I'll have to see what happens to this real quick. So this E gets transposed, and I swap the order, so that becomes this E transpose here. This E transpose gets transposed, and I swap the order, so that becomes this E transpose here. Sorry. E transpose just becomes E. And then I had this E transpose that I'll carry down. Oh, sorry, I've said E and transpose quite a lot in this last couple sentences here. And what do I end up with? I have I minus EE transpose over M, which is A. So A transpose A is also equal to A squared. And since A, so what I've really done here, I haven't touched this second A. So all I've done is operated on this first part of the product and just shown that A transpose is equal to A. So that tells me that A is symmetric. But that's not all yet. So I have A transpose A is equal to I minus E. Well, you can read it now. So I can say that's equal to I minus EE transpose over M squared. So A transpose A is equal to A squared. But I can actually go ahead and just do this multiplication as well. So let's see what happens when I do that. So I end up with, it's just the standard, first, outer, inner, last. So I have identity matrix times identity matrix gives me identity matrix squared. Then I have outer identity matrix times this, and it's negative. And then I have inner identity matrix times this. So I get two of these guys. And then the last one, I get EE transpose squared over M. So EE transpose over M, that thing squared, which I've written out here. So these middle terms are going to be the same. So I'll just write two of them. I squared is just like 1 squared, but with matrices, so I get the identity matrix back. And then when I do this product here, I'm going to get an M squared in the denominator. And then I'm going to get an E transpose, E and E transpose. So just write those four things out here. And then remember, these are just matrices, even though they're one by something matrices. But I'm free to do this multiplication in any order I want to. And so what I'm going to do is do the inside multiplication first. So I'll have E transpose E, which is an inner product, or a dot product, of a vector of M1s with a vector of M1s. So that's going to be 1 times 1 plus 1 times 1. So I'm basically just adding up 1 squared M times. So that's equal to M. And it's scalar, so I could then move that out in front if I wanted to. And that'll cancel out one of my M's that I have in the bottom. So this just becomes this M. This M will cancel out one in the bottom. And what I'll end up with is I have 1 minus 2 times EE transpose over M plus EE transpose over M, which is 1 minus EE transpose over M, which is equal to A. So this matrix A, it's got two neat properties now. If I multiply a vector by A, pre-multiply a vector by A, it subtracts the mean from each element. It subtracts the sample mean from each element of my vector. And it also has this, well, I think it's a neat property, that A squared is equal to A. And so there's a special name. This actually pops up more often than you'd think. There's a special name for matrices that have this property, and it's called idempotent. So if A squared is equal to A, it's an idempotent matrix, which is a word I'm still not really comfortable pronouncing. Okay, so now let's see what happens if I plug this back into my covariance matrix formula. So remember, I'm trying to get the covariance matrix for R. Initially, I had it as R tilde transpose R, but then I could get rid of the R tildes by using this A matrix. And then when I did the transpose the product AR, I got this A transpose A, but we've just proved that that's equal to A squared, and then that's also equal to A. So I end up with this expression for my covariance matrix for R. So I have 1 over M minus 1. That's a scalar. It's just the kind of taking the average of these squared deviations. Then I have R transpose times A times R. And then you want to do some sanity checks and every now and then when you've done a big calculation like this. So R transpose, R is an M by N matrix. So R transpose is going to be N by M. And then A, remember, was M by M. So here, these M's match and these M's match. So I'm able to do that calculation. Then the outer dimensions give me the dimensions of the matrix product. So it's going to be an N by N matrix. And that's good because on the 1 or 2 slides ago, I kind of argued at the very end that this covariance matrix should be an N by N matrix if R has N columns. But the problem with doing this is actually, so I started out with an M by N matrix, and in my example, M was a big number maybe, but N was equal to 2. And now to do this, I would actually have to compute an M by M matrix. So if M is a big number and N is 2, then R transpose and R, they're going to have 2M entries in them. But this is going to have M squared entries. So that's going to be a really big matrix. It's going to take, if I were programming it or if I were trying to write it on a chalkboard, it would take a long time to write that matrix down. Or it would take a lot of memory. And then when I do the matrix multiplication, if I've used up all that memory to store a matrix, I have to go through all that memory to do my matrix multiplication. So this is another nice thing about I can choose what order I want to do calculations in to try and minimize the amount of work I actually have to do to compute this product here. So to do that, I'm going to replace A by its definition again. And then just look at what's going to happen when I rewrite. So here, if I do this product first, I end up with an M by M matrix. And I want to avoid doing that. So sort of the obvious thing to do would be to do this times R first. So I'll take this M out. I'll write that as just 1 over M. Then the EE transpose, I'll have E here, E transpose, and then R. But I'm going to do this red calculation first. And so that's going to be 1 times M times N. So that'll be a 1 times N matrix. So it's a matrix with 1 row and N columns. And then I'm going to call that M1, and I'll stick that back here. And that's actually pretty small. So in my example, when I just had X and Y as the columns, my N was equal to 2. So this M1, even though it's a big M1, it's a 1 by 2 matrix. So it's actually only takes me 2 numbers, so it's a lot less than M squared. And now I still have to do an outer product. So the inside dimension here is 1, so that the E times M1, that's going to give me an M by N matrix. But that's still just the same size as my original R matrix. Oh, and I guess also I should point out I did this R times the identity matrix and stuck that here. Just that's where the rest of this is. Oops, here. That's where the rest of this is coming from. But the exciting part is the part on the right-hand side here. So I'll do this matrix multiplication E times M1, this outer product. And that'll give me this M2 matrix here, which is M by N. And then I can go ahead and do this subtraction here. And then when I do that, I'll just have R, which will be an N times N matrix, and I'll have to do one more matrix multiplication, and that'll give me a covariance matrix for R.